Hi, my name is Alena, and I'm going to be taking you through Spring 25 midterm question 2. So in this question, we have a bunch of true or false questions, so I'll just go through each subpart and talk about the reasoning behind each answer. So 2.1 says, the Caltopia Space Agency only allows a few critical employees to control a space shuttle's flight path, while the rest of the employees only get enough access to carry out their work. True or false, this is an example of least privilege. So recall that least privilege is basically the idea that you should not be giving out unnecessary permissions, or else this can be used against you in an attack. And this basically describes the situation we have here. So the answer for this question is going to be true. Okay, so for 2.2, EvanBot designs a system that uses HMAC DRBG with a truly random seed to generate secret keys used for symmetric encryption. True or false, based on Shannon's maxim, we should assume that the attacker knows EvanBot is using HMAC DRBG and can predict the generated secret key. So recall that Shannon's maxim is that we should assume that the enemy knows how our system works. So we actually can assume that the attacker knows that EvanBot is using HMAC DRBG. However, because we're using a truly random seed to generate the key, the attacker still can't predict the generated secret key. So the answer to this question is going to be false. Okay, for the next two subparts, suppose we have a little endian C program with a local variable char pancake 8. Consider the following GDB output after running the command on pancake. So we have some contents for pancake, and we're going to answer some true or false questions on it. So I think to make this more clear, we can kind of draw out our stack on how these contents would look. So we can draw our stack, and we know pancake is 8 bytes long and it's going to look something like this. So we have E, because we're in little endian, D, DE, F, 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 AC, 70, F, 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 0, 0, 0, 0, 0, 0, 0, where pancake of 0 starts here, and then we always fill our stack left to right and then from bottom up. So let's go through the questions now. So true or false, the value of pancake of 8 is FF. So if we go through our stack now, it should be pretty clear that, as we said, EF is 0, and so this FF would be index of 4. So this is 5, 6, 7, and then this right here, this AC, is going to be index 8. So the answer to this question is false. For 2.4, the value of pancake of 0 is EF, which we can clearly see it is. So the answer to this question is true. Okay, great. So moving on to 2.5, which is now unrelated to pancake. True or false, the first listed variable of a struct is stored at the lowest address. So this is true. You might have seen something from lecture where we have local variable int a, then we have a struct, int b, int c, and then this maybe is called s. We have int d. And we can draw out our stack diagram for this. So usually local variables, you just store them from top down as you see them in the code. So the top here would be A. However, when we get into members of a struct, we actually do it in reverse order. So we'll actually push s.c first, and then s dot b. But once we're out of the struct, we do it as normal. So the next variable that's going to be pushed onto the struct is going to be d, or the last one. So this is, important to know that when we're listing the variables within the struct, it's going to be reversed. Cool. So question 2.6, during a function call in x86, arguments are pushed onto the stack in the order they appear in the function definition. So this one is going to be false. It's going to be in the other direction. So again, you might have seen something in lecture where if we call a function foo with arguments 1 and 2, the stack here will look something like we'll push 2 first and then 1, and then, as you might expect, the RIP of foo, and then the SFP of foo. So we push them in the reverse order. Okay, cool. So 2.7, true or false? A buffer overflow vulnerability is impossible when stack canaries are enabled because canaries protect the entire stack from arbitrary overwrites. So this one is going to be false, and I mean, you even got to see this in lecture where we get to leak the canary, but there's also other ways we can overcome a canary, such as skipping over the canary with random writes or brute force guessing the canary. Okay, 2.8, true or false? CBC mode encryption in IND CPA secure, even if IND CPA secure, even if the IV is reused across multiple encryptions with the same key. So this is going to be false. You might have recalled from lecture that if we reuse the IV, then the scheme becomes deterministic, and so it's no longer secure. Okay, 2.9, true or false? RSA encryption without proper padding schemes is IND CPA secure, provided the key size is sufficiently large. Okay, similar to last question, this answer is going to be false because the padding is what makes the scheme non-deterministic. So without the padding, it's going to become deterministic and not IND CPA secure. Okay, 2.10, true or false? Rollback resistance ensures that an attacker cannot guess the next generated bit in a pseudo-random number generator. Okay, so the answer to this question is going to be false. Recall that rollback resistance just means that they can't, the attacker can't learn previous states, but this doesn't say anything about what they know about future states. So maybe they can learn, they can guess next generated bits, but they won't be able to know anything about previously generated bits based on rollback resistance alone. 2.11, true or false? Public key encryption is used in hybrid encryption because it can encrypt large amounts of data quickly. So this is false. Public key encryption is actually slow for large amounts of data. And so the idea of hybrid encryption is to actually use symmetric key encryption to encrypt your large data, and then use public key encryption to encrypt your key that you used for symmetric key encryption. Okay, and finally 2.12, true or false? One-time pads are inconvenient because the keys can never be reused and need to be at least as long as the plain text. So this is true, and this is pointed out in lecture, that one-time pads are impractical for two reasons. One is key generation. Generating a random key every single time you want to send a message is expensive. And the second point is key distribution. Because in order to communicate an n-bit message with this scheme, we'll need a key of at least n-bit, that's at least n-bit long. If we had a way to communicate this n-bit long key, then we could have just communicated the n-bit message directly to begin with, without needing to transfer this key in general. So this is true. Okay, and that is the end of question 2 for Spring 25 midterm. Yeah.